Good night, everyone, and welcome back to your channel, Fundamentals of Engineering with Mechanics of Materials, Maximum Deflection Calculation. We have solved this interesting problem with two different approaches so far. This is cantilever beam handling a distributed load of W, and we want to calculate the maximum deflection and also angle of rotation at the free end B. So far we solved it with the integration approach and also moment area approach. This time we solve it with the Castigliano's method. So if in Castigliano's method we work with the strain energy, the mass function of U is equal to integration 0 to L m sub x squared over 2 EI dx. And if we want to calculate delta at B, we need to apply a virtual load of Q sub B, which creates a downward movement, which we call it delta B. And then delta B, based off Castigliano's method, is a partial U over partial QB. The Castigliano's method used the partial derivation of a strain energy based off the appropriated load which creates that movement. So for QB, we do know that a downward movement is created by a concentrated load like QB, which creates a delta B. Likewise, for calculation of theta at B, we creates a virtual moment at B and then use the partial derivation of strain energy function, this time partial U over partial M sub B, which is the developer or inducer of that theta. So for delta we use a concentrated load, for theta we use an operator which creates theta, which is M sub B. Let's jump to the calculation of delta at B. So again, U function delta B and virtual load delta B is partial U over partial QB. And if we just cut the beam from the free end by length of x and develop the moment function, summation of moment about x goes 0, it just gives us a negative mx minus qbx load times length, and also this is a clockwise, so that's a negative one, and then wx squared over 2. So again, this is like the x over 2, and that's wx. So again, that's a clockwise, and so that's why we use it. A negative wx squared over 2 is equal to 0, and it just gives us our moment function like m sub x is equal to negative qb times x negative wx squared over 2. As soon as we have our moment function, we need to jump to our calculation for calculation of yb. So we have like our yb, and let's jump to this part. U strain energy is equal to integration from 0 to L m squared over 2 EI dx, and part delta B or y sub B is nothing but partial U over partial QB, which creates that downward movement. And let's have a closer look. If we just consider this part like a function of y is equal to x squared, then dy is nothing but 2x times dx. Let's use the same mass for this part, and it just says in the derivation of m squared over 2ei based off m is 2m over 2ei, then dm over dqb or partial m over partial qb, then dx for the integration. Use the same mass and then cancel out the term like these two cancel out with these two in the denominator, and it just gives us like yb or delta at b is partial u over partial qb, and that's equal to integration from 0 to L m over ei times partial m over partial qb dx. Then as soon as we have that part, we know our yb comes from this equation, and we have like our mx. Let's have it like this time. If this is our mx function, partial m over partial qb is just a negative x, which we got it here. And then if you replace this part, so this is m over ei comes out of the integration, and this is our m function, which just replace from moment equation, which is here. This is our m function. But be careful, because at the very beginning of the problem, this is a virtual. We don't have any QB. So this part is equal to 0 in the moment function, because this is a virtual one. There is no real QB index structure. But partial m over partial b is it just comes from this part. And if you do the math, it just gives us like, do the math and then integrate it from 0 to L. Yb is equal to delta b, and that's w, a negative downward movement, wl to the fourth over 8ei, which we also calculate delta at b based off integration and also moment area method. This is another mass solution, and that's Castigliano's method. And then if we jump to calculation of theta at b, again we have a strain energy function, develop a virtual moment m sub b at free end, and then theta at b is equal to partial u over partial m sub b, our virtual moment. Again, summation of moment about x goes 0, this time negative mx minus m sub b minus wx squared over 2 goes to 0. Mx function calculated to be negative m sub b minus wx squared over 2, and we don't need this part. And then as soon as we have our mx, we can easily go for the some partial m over partial mb. This is our m, and a partial m over mb is just a negative 1. As you can see here, that's only negative 1. Partial m over partial mb is just a number negative 1. Again, theta at b is partial u over partial virtual moment, and it just comes from the same equation. And then again, this is m over ei. This is the moment part, which comes from this equation. And negative 1, it just replaced from partial m over partial m over partial mb. And be careful, there is no mb. This is like a virtual moment. So in the reality, we didn't have any one. So we need to equalize that to 0. And then if you do the math, it just gives you, if you replace mb with 0, this part transfers to the moment part, and this part, it just comes to derivation of m over mb. And if you do the math, it just gives you a theta is equal to negative wl cubed over 6ei, which we calculated with the integration method, the same parametric value, and also with the moment area method. If we have a combination between these three solutions, so solution 1 was the integration method, and solution 2 was the moment area method, and this time solution B was the Castigliano's method. You can use either of these solutions. All of them are interesting and nice, but the first and last are math solutions, and the second one is the geometry solution. I do recommend to solve it from all of them to master the problem, but in terms of exam or fast calculation multiple choice exams, you can use the second one, which is fast approach. Thank you. We'll solve more problem related to beams relations in next videos.